eventually Shor's algorithm. But before that, we need to review some math. And the first thing is the nth root of unity. You guys should have learned that, but I forgot it after a few years of study. So I am sure that it will be useful to discuss. First of all, just remind you, e to the power I theta equals to cosine theta plus I sine theta. Okay. There was a very beautiful equation, right? When theta equal to pi, you have I e to the power I pi equals to, is this 1 plus 0? Was they talking about this? Yeah, you see people print this on their shirt, right? Because this equation has all the most important number in math. E, I, pi, 1, and 0. Negative 1, I always say something wrong. Okay, then I'm right, okay. Because it's negative 1, so I move 1 to here, plus 1 equal to 0. Now we get every number, right? Negative 1, you're right. Cosine pi is negative 1, so it becomes plus 1. Right? So very beautiful equation. I don't know if you appreciate. I don't. And you don't need a. So, yeah, I will do that. So, okay, so this equation you need to remember, right? If you don't find, put in your cheat sheet. That's the first thing. Second thing is, let's go back to the nth root of unity. If I ask you to solve this equation, x to the power n equal to 1. Now, x to the power 2 equal to 1, what are the solutions? 1 or negative 1. Then, how about x to the power 4? What are the solutions? Yes, not just 1 negative, you have 1, negative 1, I, and minus I, right? So, yeah, you do have 4 roots. So, x to the power n, you have how many roots? You have n. You have n roots, right? And what are they? X equals to e to the power I 2 pi divided by capital N times k, with k equal to 0, 1, 2, all the way to n minus 1. Right? We are not going to study this, but you should know this equation. For example, this figure shows capital N equal to 12. And this is a complex plane. This is real, this is imaginary. And then you ask about what is x, x to the power 12 equal to 1. What are the solutions? You have all these 12 solutions. Okay? And what is the meaning of omega here? Here is very important. We set omega equals to e to the power I 2 pi over n. It's easy to memorize. All you need to remember is just that 2 pi I, right? E to the power 2 pi I divided by capital N. So this is omega. And if that is the case, then it means that x equals to omega to the power k, with k equal to 0, 1, all the way to n minus 1. Is that okay? All right, so just take it for granted. If you forgot, you can go back to review. For example, if it is 12, n equal 12, I can give an example. N equal to 12. Yeah, the solution are shown here. They are omega to the power 0, omega to the power 1, all the way to omega to the power 11. And what is omega? Can you tell me? E to the power I 2 pi. Thank you. You say pi over 6, but I keep 2 pi and then over 12. It's the same. Yeah, very good. 2 pi over 12. So that is the nth root of unity. Okay? And how we can check, right? Check to see if it is correct. because I claim that this is the solution, right? So omega to the power k, for example. Omega, actually, my cheat sheet is not good. Let's say omega to the power k, right? I plug in x, right? This is x. X equal to omega to the power k, right? So I put into this equation, x to the power n. And you know that I can swap this index, right? This become omega to the power n and then power k, right? Make sense? And again, what is omega? I need to write it down. It's e to the power I 2 pi divided by capital N. And then you say to the power n and then to the power k. So n and n cancel, you get e to the power I 2 pi. But what is e to the power I 2 pi? Go back to the equation. Cosine 2 pi plus I sine 2 pi. What is cosine 2 pi? 1. What is I sine 2 pi? So this is 1, right? So 1 to the power k equals to 1. So indeed, this is correct. Omega, this to the power n give me 1. So indeed, omega k to the power k is the solution of this equation. Okay? So this just to help you to practice the index again and those you have forgotten. But after all, the main point you want to learn here is that the nth root of unity is omega to the power k, and omega is e to the power I 2 pi over capital N. This is what you need to memorize. Okay? Any questions? Now, if no, we will continue to recall some properties of this nth root of unity. What happens if I add omega to the power 0 plus omega to the power 1 plus all the way to omega to the power n minus 1? Just look at this figure. What do you think if I add them all together? Remember, this is on a compressed plane. What happens if I add them all together? I add this number together, becomes, someone says 0. Why? Because the compressed number on the 2D plane, on the compressed plane, is just like a vector, right? It has a real part and an imaginary part, like x and y part. Look at this, they are all symmetric. You have 0, then 5. Otherwise, plus minus, they all cancel horizontally and vertically. It's just like a force. You have a table, evenly distributed. Everyone try to pull away from this table. You get a net force equals 0. The table is not moving, the round table, right? So intuitively, you can see that if I sum them together, I will get 0. Okay, so this is one property. I expect it to be 0. But of course, I cannot be so hand-waving. I'm going to use the geometric series equation, which is like this. The ratio from this term to this term is omega. Each term increased by omega, right? Omega 0 times omega to the power 0 times omega becomes omega to the power 1, times omega becomes to the omega to the power 2, then times omega becomes omega to the power 3. This is a geometric series. And there's an equation. The sum is 1 minus the ratio to the power of number of terms divided by 1 minus the ratio. Let's recall. And this is really something you can ask ChatGPT, right? You don't just go ahead to say, what is this? Why this is true? Yeah, then it tell you this is true. You will say, oh, someone say this related geometric series. What does it mean? What is geometric series? What is that, right? Then you learn a lot. Right? Just recall a geometric series. You have, let's say, A we need to start with the first term. Let's say 1, A squared, A3 all the way to AN. What is the sum? The sum equal to 1 minus A to the power N divided by 1 minus A, because their ratio is A. Okay, go back to check it, and that is what it is. What is omega to the power N? We just say that. What's omega to the power N? Because it's the nth root of unity, right? So to the power N is 1. So this 1 minus 1 divided by 1 minus omega. So what is this? 0. Okay, fine. So the first thing we have learned is that we sum them together, you get 0. Second property, I have an integer, L. Okay? I have another summation, omega to the power 0 times L. This is multiplication. Okay, this is not any other logical operation. Plus omega to the power 1 times L, plus omega to the power 2 times L, plus all the way to omega to the power n minus 1 times L. So nothing is changed, still omega 0, omega 1, but the index is multiplied by a constant integer. Okay, what is this? Some people say 0. The now depends. Because if L equals to 0, what is this? It's equal to, because everything is 0, right? Becomes 1 plus 1 plus 1 all the way to, you have n1. So I should use capital. Which is what? N. Okay, if L is 0, it is N. And now we can start talking some terms that might be relevant. We call this like constructive interference. Like the wave. Now I have many components. They all give me the same value. Constructive interference. I get a peak there. And what does it mean in this circle? It basically is saying that all the points will just coincide on this same point because you times 0, right? And then the other one, if L not equal to 0, that is what you just said. Why? Because now the sum becomes the first term, which is 1, minus the ratio of the terms. The ratio of the term is omega to the power L instead of omega. And then the whole thing n. And divided 1 minus the ratio. Okay? And of course, this I can swap it because I already say that this is just equal to omega n to the power L divided by 1 minus omega L. And then omega to the power n is 1, so this is just 1 minus 1. And luckily, because L is not 0, so it's not 1 minus 1 in the denominator. So this is 0. What would you call this phenomenon? Thank you. Destructive interference. And now we'll start getting some idea. Maybe in our future so-called quantum Fourier transformation, we are going to use this. Do some constructive and destructive interference to get the answer we want. Okay? Now we also have another property to go through. Omega n minus 1 equals to omega minus 1. And it's not difficult to understand. Omega n minus 1, which is omega to the power 11, right, in this case, is the same as going clockwise, which is minus 1. Okay, but what does it mean, right? How do we prove? We can prove it. And it is easy to prove because omega n minus 1 just equal to omega n divided by omega, right? And what is omega n to the power n? again, is nth root of unity, so it's 1 over omega. So this is omega to the power 1. Nothing special, but we are going to use this property in the future. So again, if you don't know how to prove it, it's fine. But you need to know that you need to use this equation. Particularly, what we care the most is about constructive and destructive interference. When you see a sum over the term, you know, oh, okay, this term is going to be 0. These are going to be 1. And later you will see in those phase estimation algorithm, Shor's algorithm, you will see many of these terms, it becomes 0, okay, I can ignore it. It's not going to happen. And that's why the constructive interference part will give us the answer. Any questions? So before we go to quantum Fourier transform, I want to go to discrete Fourier transform, which is purely classical, but it helps us to understand quantum Fourier transform. Okay? So what is a discrete Fourier transform? It's very simple, actually. In our class, we make it very simple. Given a vector, it's n-dimensional vector, okay? It is like this. This is a vector, x0, x1, all the way to xn minus 1. Just a vector, any vector, okay? It can be the vector of the student name of our class, for example. And you say you do a discrete Fourier transform. Then you will transfer it into another vector. And it's so simple. That's it. Transfer into another vector. y0, y1, all the way to yn minus 1. And that's it. A transfer a vector to another vector. So nothing special about discrete Fourier transform. And how do you transfer transform one vector to another vector? You use what? That's what we have been talking about in this class. Matrix, operator matrix, right? So, of course, I need to define, right? So now I am going to define what is discrete Fourier transform. I'm going to transform it with this equation, yk. The kth component of the second vector is equal to 1 over square root n, summation j equal to 0 to capital N minus 1, xj, omega to the power negative kj. It's very long. Yeah, you will get scared at the beginning, but then you find that it's very easy. Basically, it's saying that any component, y component, is a summation of the x component. Okay, you're transforming, all the original vectors should contribute to me. But they don't have the same weight. They are weighted by omega to the power negative kj. And omega is the nth root of unity. And you just raise it to the negative kj. What is k? K is my identity. I'm the kth component. J is the identity of the x component, right? So first component, you contribute to me by multiplying my index with your index. And second component, you contribute to me, multiply my index with your index. You keep doing this, you add them together. And that's it. And it's not difficult to memorize. And of course, I can expand it. J equal to 0 to n minus 1, summation, right? Xj is still the same. But here I just expand the nth root of unity. It was 2 pi I divided by capital N, right, omega. But now I have negative, right? So I have k times j times 2 pi I divided by capital N. And that's it, right? So I don't know, you probably learned about discrete Fourier transform before. I did also, at that time was so confusing or very difficult, but now you look back, it's very simple. Just remember, you transform something, my component must depend on every original component. So you just add all of them together, but they have different weights. Again, it is nth root of unity to the power of negative its index times my index. And we need to normalize by 1 over square root n. Now, this one looks complicated, but we can also write it in the matrix form. This is the result, y0, y1, all the way to yn minus 1. And this is the input. x0, x1, all the way to xn minus 1, right? And I told you this is nothing but just a big matrix. And let's look at this. What is y0? It must be equal to this row times this column, right? And this row means this one times this plus this one times this plus this one times this, right? So obviously this is what? Omega to the power negative 0 times 0. Omega to the power negative 0 times 1, all the way to omega to the negative 0 times n minus 1. And this will fulfill this equation because I'm talking about k equal to 0. So it's equal to omega to the power negative 0, which is k, times 0, and then you times x0, times 1, and then you times x1, times negative n minus 1, then you times n xn minus 1. Do you see that? This times this is just equal to this equation. Do you see that? Any questions? Is that clear? Right? So basically, it means that the row has the index of y because it's determined by y. The column has the index of x. So this is row. Right? And then you keep doing that until the last one. Yn minus 1, of course, is negative n minus 1. K is n minus 1 times 0. Omega negative n minus 1 times 1, all the way omega negative n minus 1 times n minus 1. Right? Because now k equal to n minus 1, then it's equal to x0 times omega to the power n minus 1 times 0 negative. x1 times omega to the power n minus 1 negative, right? So just check it. It turned out to be correct. I missed one thing. What do I miss? Thank you very much. 1 over square root n, right? And this represents that equation. Now, if this is like this, I can also write it as this form. I say I have vector that is y is equal to x times a matrix. And this matrix, I can call it omega, but I also can say it is omega negative kj. What is the meaning of this? We talked about this before as a shorthand, right? When I just say that the matrix is just a parenthesis and then a number. What does it mean? It means the kth element, kth row, jth column is omega negative kj. That's the element. Okay. Yeah, of course, you might also see people just write y equal to omega because it's a matrix and then x. After all, that is what it means for all of them. Okay. Maybe I will talk about the example next time. And let me know if you have any questions.